Log on, tune in, find out. Another good idea from Cambridge.
Who will actually tell us about Deligne-Lusztig varieties and cyclotomic Hecke algebras.
Okay, thank you very much. Thank you for the chance of speaking here. So actually, this wrong title is the motivation for the study of Deligne-Lusztig varieties in this context. And so I need to spend some time explaining the motivation. And I hope I will get to the technical stuff about Deligne-Lusztig varieties, so we'll see. The idea is that you look at Bourret's conjecture for blocks with abelian defect groups in the case of predictive groups. So to make things simple, I will just consider the conjecture for the principal block, which says that if the L-silo of some finite group is abelian, then there should be a derived equivalence between the principal block of the normalizer of the silo and the principal block of G. And derived equivalence, so okay, first, as usual, I have a modular system. So I consider the blocks of the group algebra over some extension of ZL. And derived equivalence means that there should exist a tilting complex, which does realize this equivalence, means a complex which has no hom with a shifted complex, and such that the endomorphism, the complex is a complex of bimodules, and the endomorphism of the complex on one side gives the algebra on the other side. And the point is that for a finite predictive group in characteristic L different from P, P different from L, when L is not the defining characteristic, then this tilting complex should actually be the cohomology of some Deligne-Lusztig variety. And the other interesting fact is that this endomorphism of the endomorphism of the complex with the other block, it should actually come through a cyclotomic equialgebra, because what will happen is that this normalizer of a silo is the silo semi-direct this quotient, and this quotient is a complex efficient group. But you won't find the complex efficient group acting on the cohomology, but just some Hecke algebra related to it. Okay, so this is a story that I will go on. Okay, so first I fix some notation for reductive groups. So I take a connected algebraic group over the algebraic closure of a finite field. In order to cover the real enthusiastic groups, I just choose an isogeny with finitely many fixed points. And the fixed point is what is called a finite predictive group or a finite group of Lie type. Actually, if you take a group which has a connected thinking diagram, then this isogeny is related to a Frobenius. Some power of it will be a Frobenius. And I need to record which power it is. It's usually the square or the cube, which is a Frobenius. And so this defines some number delta. And it also defines number q, which is the power of square root of p. This is what happens for the Suzuki and Rie group. Okay. Now I will also have this notation. I choose a pair of a maximal torus and a Borel subgroup which are f-stable. And I look at the Val group relative to this maximal torus. Then, since I choose this pair f-stable, I get an action of f on this Val group on the vector space, which preserves the set of positive roots. So it gives rise to some automorphism. And actually, the action of f on this complex vector space, which I will consider, tensor x of t with c, is of the form q times phi, where q is a power, is this number I've introduced, a power of square root of p, and phi is a automorphism of finite order of the vector space, which normalizes the Weyl group. So actually, this abstract situation will be important. I have the Weyl group, a reflection group in a complex space, given with some automorphism of finite order. Okay, and the first thing I want to explain is that this situation is already enough to start and seeing that there is a complex reflection group attached to an abelian silo. Because you have a formula for the order of the finite predictive groups, which is purely in terms of invariant theory of the Weyl group. So this Weyl group is a reflection group on this complex vector space. So the polynomial invariants form a polynomial algebra. And also you can choose these fundamental invariants to be eigenvectors of phi. And so this defines two sets of numbers. This defines the degree of the invariant and the eigenvalue of phi on this invariant. And with this data, you have a formula for the order of the finite predictive group, which is purely in terms of this invariant data. So there are elementary proofs of this, but in the context of my talk, a nice proof is to remember that the cohomology of G over B is a co-invariant algebra of the Weyl group. And so if you use the Lefschetz formula starting from that, you can recover this formula. Okay, but so we have a decomposition, a polynomial decomposition of the order of GF. And the next step is to try to decompose into prime polynomials. We want to look at the silo, so we want the prime factors. But the first step is to look at the prime polynomials. So if we decompose in prime polynomials, we get this, well, it's a product of cyclotomic polynomials. And a given cyclotomic polynomial, I want to record how many times it occurs. So it occurs a number of times, which is the cardinality of this set. It's a set of degrees such that you have this equality. If you take a primitive this root to the degree, you get this factor attached to it. So if you want, if there was no twisting, if I had a split group, there would be no phi, and the number of times this number A of D would just be the number of degrees divisible by D. Okay, but I claim that here you already see something, some complex reflection group appearing because of the connection with the following theorem of Lehrer and Springer. That if you take now an arbitrary reflection coset, that is, you take any complex reflection group, and you take some elements which normalize the reflection group, this number A of D is actually the dimension of a maximal zeta D eigenspace of some element of the group. So it occurs naturally. And furthermore, two such maximal eigenspaces are conjugate under the group. And here you get a complex reflection group. If you take a maximal eigenspace, and if you look at the normalizer of the eigenspace modulo the centralizer of the eigenspace, so it's a linear group on the eigenspace. And the linear group is actually a complex reflection group. And the reflection degrees are these degrees A of D. So actually, to a prime factor of this order, we see we can attach some reflection group. And it's not purely formal, because now take an element which has this eigenspace of maximal dimension, and take the torus of type W. Then this will be a factor, this phi d to the A will be a factor of the characteristic polynomial of W. And to this factor of the characteristic polynomial, there corresponds some stable sublattice, so it means some stable torus. So we have, and this torus will have order this polynomial. So actually, to a prime factor as a polynomial of the order of the group, we can associate a torus, and whose order is this prime factor. So this is a kind of geometric version of the CILO. We have replaced a prime number by a prime polynomial, and I have replaced the CILO by the torus. But actually, it is related to the actual CILOs. So in this situation, we say that this torus is a phi d CILO. And from the previous theorem, we can find that all these phi d CILOs are actually conjugate. And actually, what is more, that if you assume that the L CILO of G is abelian, then this L will pick a unique, there will be a unique cyclotomic factor of GF divisible by L. So L will pick a unique phi d and will pick a CILO. And so actually, there will be a unique CILO, phi d CILO, which contains the L CILO. So actually, when we pick a prime number, we pick a torus, we pick a we pick this kind of geometric CILO. So it means that when we choose a abelian CILO, we choose this unique torus. So it means that the centralizer of the CILO we have chosen is a centralizer of a torus, so it's a Lévy subgroup. And it also follows that if you look at the normalizer of the Lévy divided by the Lévy, which is the same as a normalizer of this CILO divided by the CILO, you get this complex efficient group. So we have this complex efficient group associated to the choice of an abelian CILO. And so we know also its degrees. And if you start from, if you start from a file group, and if you pick a D, usually the complex efficient group you get is really complex, not real at all. It's really the series of complex efficient groups. Okay, and also in this situation, it's not difficult to see that the principal block of the normalizer of the CILO is just the algebra of the CILO extended by this complex efficient group. So actually, we want to find this as endomorphism of a complex corresponding to the block. Okay, so this is where the Deligne-Lusztig varieties will occur. So I give you a crash course on this variety. They are attached to the situation where you choose a Lévy subgroup of some parabolic subgroup with a unipotent radical, and when L is F-stable, but P is not necessarily F-stable. And this situation, so that's not exactly the division you see in books, but I like this one. It's completely equivalent to the one you see in books. So the Deligne-Lusztig variety is a set of cosets of the unipotent radical, which intersect non-trivially the transform by the Frobenius. So with this definition, you can see that you have a left action of GF, because this condition is stable by multiplication of the left by GF, and you have a right action of LF, because LF goes through V. What you can also see is that if V was F-stable, then by Lang's theorem, you can see this is just the discrete variety of cosets, rational cosets. So it is just this variety GF over VF. Okay, so once you have this variety, you define the Deligne-Lusztig induction by looking at the cohomology complex. So you take this virtual vector space, which is alternating sum of the cohomology with a structural sheaf. This also, so it is a module with an action of GF on one side and LF on the other side. And this is what gives the Deligne-Lusztig induction. So in the particular case where the V was F-stable, it would just be this permutation module, which, as you know, gives Harry-Chandra induction. Okay, so in this situation, I remind you that to this silo we associated a Levy, and the conjecture is just that the chain complex associated to this variety is actually a tilting complex. So this is just a conjecture in this case. Okay, so now I will present it in a slightly more convenient way by using another Deligne-Lusztig variety, where this time you look at the coset of parabolic subgroups. So in this variety, you still have an action of GF, but you lose the action of L. It becomes trivial. But what happens is that this previous variety is a covering on the new one, with the fiber being the Levy. So it means that when you look at the direct image of the structural sheaf on the variety above, it will decompose exactly according to the blocks of the algebra of the Levy. And so it's a bit more convenient because in the previous case, yeah, I forgot to say it, but it was written, you have to cut this cohomology complex by the block you are looking at. Because, of course, the cohomology complex that had the previous slides contains all the representations of the Levy. I had to cut it by the right block. This time, I can just choose the sheaf corresponding to the block I'm looking at. And if I look at the, if I cut the previous cohomology complex by this right sheaf, I just get the cohomology of this new variety with the right sheaf.
What is F?
So I say that the direct image splits into sheaf corresponding to each block. So I give a name, the name I give to a sheaf corresponding to the block I'm looking at. So in this case, I will just choose a sheaf corresponding to the principal block. And the conjecture says the same, but about this time the whole chain complex not cut of this variety with this sheaf. So the conjecture says, I just recall again what means a tilting complex. So it says that there are no x between different cohomology groups, and that the endomorphism of this complex is equal to my block, which is this group algebra. Okay, so that was the motivation, but actually what I will study is still a simplified version of this conjecture, because this is quite hard. If you want to study this, you need to look at the cohomology with coefficients in some sheaf, where there could be torsion. And the complete story for this kind of sheaves is only known in dimension 1 and 2. There is some work of Raphael Rouquier where I could compute in small, for groups of rank, groups of rank 1, actually. You can only compute everything. So this is a bit difficult, but we will look at some consequence of this conjecture, which is a bit simpler and still gives a good feeling. So first, I won't look at the principal block. I will just look at the subsheaf, which is a structural sheaf. And so this taking the subsheaf, it means only looking at the trivial representation of L, means that upstairs on G, I will only look at unipotent characters, which means I will look at some shadow on unipotent characters of what the conjecture is saying. And the second thing that I will also forget about O and go to the field. I will even go to the QL bar to have no problems. And so there still remains a conjecture in this case. This time, these are ordinary representations of my groups, these cohomology groups. I still want to see that they are disjoint. For the various cohomology are disjoint. And the second thing is that I would like still to show that the endomorphism algebra of this time, the endomorphism algebra of the complex, since the groups are disjoint, is just the endomorphism algebra of the direct sum of these cohomology groups. And I want to see that this endomorphism algebra is isomorphic to the group algebra of my complex reflection group. Okay, now the interesting part is that I won't able to show, so I remind you that in this case, this vector space we were looking at is exactly the module corresponding to this induced representation, the Deligne-Lusztig representation. Yeah, and now I say I won't be able to show directly that the endomorphism algebra is this group algebra, but what I will find is that I can make some braid monoid which is attached to this complex reflection group act on my variety, and it will act on the cohomology through some cyclotomic equialgebra. And this cyclotomic equialgebra is what is isomorphic to the group algebra. So this will be so this is the end of the motivation. And now we can start looking at the situation. So first, I need to fix some notations about the braid groups of complex reflection groups. So I remind you, first the definition. The braid group is a pi 1 of this configuration space, where you take the regular points, which means the place where W acts regularly, or if you want, the complement of the hyperplanes. So it has been shown by various authors I will cite that this group can be generated by the same number of elements as the reflection group can. But now you have to know that when you take a complex, irreducible complex reflection group, it cannot always be generated by dimension of V reflection. Sometimes you need one more. And so the braid group can be generated in the same way, but sometimes you need one more than the dimension in V. Also, the generators are elements which just lift reflections, called braid reflections. So maybe I can explain to you exactly how look the generators. So I will draw a complex hyperplane in dimension 1, because that's the only one dimension you can see something. So this is a complex plane. This is some hyperplane. And now I have my base point, and I want to define something relative to this hyperplane, which will be similar to a reflection. So what I will do, I go very close to this hyperplane. I apply some reflection, and I do a small circle around, and I come back by some reflection. And now in the quotient space, this is actually a loop, because in the quotient space I have identified these 2 points, which are the image by reflection. And the element I got here is well defined up to conjugacy in the braid group. I define a well-defined conjugacy class of elements in the braid group. Is what I call a braid reflection, which lifts this reflection here. And so this this braid group can be generated by these braid reflections. And it has also been shown that the relations are homogeneous relations, where so it's a bit similar to the presentation of the usual braid groups. You have homogeneous relations between two words of the same length, but the difference is that in the Coxeter case, the words always look like that, but they can involve 3 generators in the complex reflection case. And so these are theorems of Broet-Mallet-Rouquier, the fact that you have this kind of picture. And the presentation, there are theorems of basis, and I also did some competition with David Basis for some of the groups. In this paper, you find the presentation for the braid groups corresponding to the imprimitive infinite series of complex reflection groups. Okay, and so by my construction, one of these braid reflections, the image in the reflection group, is a reflection with non-trivial eigenvalue is this particular primitive root of unity. And you get a presentation of the reflection group if you add to this braid relation the order relations corresponding. Okay, so this situation is to remind you of the definition of the complex of the Hecke algebra corresponding to complex coefficient groups. So we mimic the usual definition for Coxeter groups, where you quotient the Hecke algebra by deformed version of the order relation. So here it's the same. You quotient the braid group algebra by some deformed order relation. Except this time we deform with the maximum number of algebraically independent parameters and to get the most generic Hecke algebra. We also have we'll have some more specialized algebras. So just as for the Coxeter group case, you have an algebra which will specialize to the complex group algebra when you specialize the parameters to the proper eigenvalues. Now the situation is not so nice for the properties of this algebra. So it is known for the infinite series that it is a symmetric algebra with a canonical trace which specializes to the trace on the group algebra. But for the exceptional groups, there are a few cases where this is not yet known. But it is conjecture. And also the same characterization of the trace as in the case of Coxeter group is also a conjecture. So the characterization should be that it should be possible to lift the complex groups inside the braid group, so that when you go to the Hecke algebra, you get a basis on which the trace is 0 except for the identity element. And so it's also a definition which has been shown to work for the infinite series, but it is conjectural that this can be made to work for the exceptional groups. Okay, and now I want to define a particular class of algebras, which is actually the algebras that Brouwer calls cyclotomic Hecke algebras. Because people have seen that people tend to call cyclotomic any Hecke algebra which has something to do with the complex coefficient group. But actually, in Brouwer's mind, cyclotomic Hecke algebra should be some very specific kind of algebra. So it's the following algebra. So yeah, first to define this algebra, I should explain that Gunther Mahler has computed under which extension this Hecke algebra corresponding to complex group split. And okay, to have them split, you need to extract some roots of the parameters. In the real case, you extract square roots, but in general, the order of the roots you have to extract correspond to the order of the group of roots of unity in the field corresponding to the complex coefficient group. So anyway, you need to extract some roots. And if everything works well, we'll have that if you split the algebra by choosing some roots of the parameters, then the algebra will become isomorphic to the group algebra over the same ring if you extend sufficiently. Okay, and in particular, this will hold if you take a good specialization. If you specialize the parameters at some bad things like roots of unity, probably you won't get a semi-simple algebra. But if you take a good specialization, then this will hold. And in particular, if you have a specialization, specializing some variables that you can still specialize to the group algebra, is going to be a good specialization. Okay, so cyclotomic Hecke algebra is going to be a good specialization because you are going to specialize the parameters to the powers of one indeterminate times root of unity. And such that if you specialize this indeterminate to zeta d, you find the group algebra. So actually the definition is that it's a zeta d cyclotomic Hecke algebra. So it's some one variable Hecke algebra, such that when you put q equals zeta d, you get back the group algebra. And so Brouet wanted that this only would be called cyclotomic Hecke algebra. And you see why cyclotomic, because of cyclotomic numbers involved in the definition. Okay, so this was to phrase the conjecture now in this context. So there should be a Brouet monoid which generates the Brouet group of this complex equation group that you have attached to the situation, and which should act on the Deligne-Lusztig variety, and on the cohomology, it should factor through a zeta-d cyclotomic Hecke algebra for this group. And even we want that the character of this virtual module gives the canonical trace of the algebra. So this is the whole conjecture in this context. Okay, so now I will try to explain what we know about this conjecture and what is this monoid. So I will simplify again, so not to have it too complicated just for pedagogical purpose. So I will just look at the case where the levy is a torus. It will be a bit simpler to explain what happens. So this means that we have an element in the Val group with an eigenspace, which is times the centralizer is trivial. And so this means that this complex equation group is just a centralizer of my element. And okay, so these elements were studied in a paper by Springer about regular elements in a reflection group, which dates from 75, I think, this paper of Springer. And so if you want, they are just the elements which have an eigenvector outside of all hyperplanes. Okay, so if you take a regular element like this, now if you look at the Deligne-Lusztig variety, so in this case, it has a simple description. So this W corresponds to the class of the torus we have taken. And if you have a torus of class W, and if you choose a Borel subgroup containing the torus, it will be in relative position W with its transformed by the Frobenius. Relative position means, as usual, that you can transform this pair to this fundamental pair. You take the F-stable Borel, you have chosen once and for all, and this pair is conjugate to this pair. So in this case, the Deligne-Lusztig variety is just a set of Borel subgroup in relative position W with a transform by F. Okay, this will be useful to explain how to build this monoid. Okay, but another question is that here you have a class of elements, and actually to define the variety, you must choose a particular W. It corresponds when you have this torus of choosing a particular Borel subgroup which contains the torus. The variety dependent on a pair T inside B. And this data corresponding to choosing W in the class. And there are many possibilities. When you have a class of regular elements, there are many possible W's to choose. And so I will make some historical explanation of how we found which W to choose. So it started with some computation of Gunther Mahler, because at that time already we conjectured that there should be some Hecke algebra inside this cohomology. And actually you can guess the parameters of the algebra because since you assume that it gives you the canonical trace of the algebra, it means that the dimension of the components of this character have to be the generic degrees of the algebra. And if you know the generic degrees of a Hecke algebra, you can guess the parameters. So now if you know the parameters, you can also find what is the eigenvalues of the Frobenius, because the Frobenius will be some central element in the algebra. You can also guess what it is. And you can find what is the eigenvalues of Frobenius. And so from the computation of Gunther-Mahler, he found that the eigenvalue of Frobenius of maximal module should be this module, 2 length of W naught divided by D. But we also know that the maximal eigenvalues of Frobenius should be correspond to the dimension of the variety. So it tells you something about the W we want to choose. It tells you that this element W should have this length. So this was some confirmation actually of some other way of conjecturing what is W that we had by studying some theorem of Springer with Michel. We also found some other way of choosing such an element. So I remind you, in the Coxeter case, the bread group has just the same presentation where you drop the other relations. And this means that you can have a canonical lift in this case. You just lift this to these. And since by Matsumoto's theorem, to reduce expression can be transformed by the bread relations, we have a well-defined lift into the bread group. Okay, and you can also lift the action of the automorphism by just making it acting here like it acts here. And in this notation, if you lift the longest element and you take its square, you get a central element in the bread group, and which actually is a generator of the center of the pure bread group. And what we could show is that if you take a dth root of this element, then the image is a regular element. And conversely, in the class of regular elements, you can always find some element which, when you lift it this way, becomes a root. Okay, so from the previous slide and this one, it was a natural conjecture that the proper Deligne-Lusztig variety should be for a W which is a root of pi. So we are looking at Deligne-Lusztig varieties for W which are roots of pi, and we want to construct the action as on bread monoid. Okay, so now I will explain how we can have some elements, some endomorphism of this Deligne-Lusztig variety. So we want to find GF endomorphism, some which commute with G. Well, we have a very simple one, is F. F is such an endomorphism. But we will extend F to a class of other morphism. Okay, by the following process. If you have a decomposition of W where the lengths add, then by the Brugha decomposition, you find that there is a unique Borel subgroup which has its relative position, X on the left and Y on the right. So when you are given an element B1 of this variety, you have this B2. And if by chance the length will also add when you switch things, when you put Y, phi of X, then we know we have these relative positions. And if the length add, at the end, we have constructed an element of this other variety, Y phi of X. So we have constructed some morphism from XW to X Y phi of X, which is GF equivariant. And if in addition X was centralizing W, then we would get a GF endomorphism of W. So this looks very special, but we'll manage to make it more general. So yeah, we should notice that if you take the morphism dW corresponding to W, it just sends it's just a Frobenius. And yeah, at the start, yeah, I should also say that the group is split, because if the group is not split, W is not necessarily stable by F, and actually the elements you will get is F to the delta. You can represent F to the delta. The element W will not represent F, but some power of f which leaves W stable. Okay, so the problem is that we need very specific conditions to be able to have this morphism. And we would like to have much more morphisms. And for this, the idea is to generalize the definition of the variety. So instead of considering varieties attached to one element in the Weyl group, we consider varieties attached to sequences of the elements of the Weyl group. So first, just look at this variety of Borel subgroups. You take a sequence of Borel subgroups so that each one is in position Wi with the next one. And now it was first observed by Deligne that such a variety actually doesn't depend on the actual sequence you have taken, but it only depends on the lift of the sequence to the Borel group. It's actually a variety parameterized for the Borel group. So to see this, you notice that if you can, if the lengths add between two consecutive elements, then you have a canonical isomorphism considering of dropping, replacing a pair by the product, which corresponds just to dropping one Borel subgroup. And what Deligne shown actually is that over all the possible decomposition of an element in the Borel group into reduced elements which leave elements of the Weyl group, the set of isomorphism is transitive. So it means that there is a well-defined, this variety is well-defined, attached to an element of the Borel group actually. Okay, but now, so when you have these varieties attached to relay the Borel monoid, then we can define something more general. First, we define the Deligne-Lusztig variety, which corresponds to that, which is intersecting this variety with a graph of the Frobenius. We just ask if the last Borel is Frobenius of the first one. And yeah, by the way, so you define these varieties on the Borel group, and we have a conjecture with Digne and Rouquier that we could prove in type A2, not much, but it's already a start, that the cohomology should be a class function on the Borel group of these varieties. So that's, I think, difficult question, but interesting question about these varieties attached to the Borel group. So now we have something more general, because if we take a divisor in the Borel group, then we can go from this variety to this one always. So what might happen in the previous situation, it might be that the length of these two elements don't add, and we could not define the morphism before. But now we are in the Borel group, we don't care about this, we just, this element might not be reduced, but we can still consider this variety. So we have morphism which have defined all the time. And we can do something more general. Now you consider a category which mimics the set of varieties. So it's a category whose objects are elements of the Borel group. And when you have a morphism between an element and its conjugate, whenever the element divides in the Borel monoid this. So as I explained, in this situation, when you have an element like this, you always have a morphism from one variety to the other. Now, if you look at these categories, you can get many more endomorphisms, because it could be that you start from the variety xw, which is decomposed in xy, then you go to x y phi x, then maybe you can still go on. You have some other decomposition. This is x prime, y prime. So you can go to x y prime phi x prime. You can maybe a long way, and maybe you come back after a while to the initial variety. And now we can also use this situation, because we have a category. We can use this situation to have an endomorphism of the variety. And so the endomorphism of an object in this category will give you now endomorphism of the variety. So now we can state the conjecture a bit better, decompose in more steps. So we start with a root of pi. And so the first conjecture is that if you take the endomorphism in this category of the object W, you get something which generates the centralizer in the braid group. So we hope that we have enough morphism by the previous process. The second step that we would like the centralizer in the braid group to be actually isomorphic to the braid group of the complex coefficient group we are looking at. The third step is that we would like the action of this braid group to factorize to a cyclotomic algebra for this complex coefficient group, such that the trace is a canonical trace. And finally, you have to remember we want the cohomology group to be disjoint. Okay, and now in this program, we can prove a few steps. So we are not completely hopeless in this program. So I will explain what is proved in this, how to prove a few steps. Yeah, something I want to point is that here I was talking about actually a monoid, because the elements we can construct in the first step, they will be in the positive monoid. But since they are factor of the Frobenius, because when you compose such a morphism, you can get the Frobenius. They are all factors of the Frobenius somehow. And the Frobenius is invertible in the cohomology. So the action of the monoid will become invertible in the cohomology. So you can indeed have this group acting. So this program is well defined. Okay, and what do we know? So the first step is that we can show, so the first step is to show that the monoid generates this centralizer in the braid group. Okay, and we could show it at least if phi equal 1, it's a theorem. So this theorem basically, yeah, I did not explain enough. To show that the endomorphism generates the centralizer, you have to show that any element of the centralizer, so you have to show that in this category, well, sorry, what do you have to show? Because yeah, I'm saying that you have to show that two roots are in the same connected component. So y is the same as showing the centralizer is right. Yeah, because if you take an element of the centralizer, it will map a root to another root. And if we show that this other root is the same connected component in the category, this will show that you have some morphism going from one to the other. And so it will show that the element of the centralizer can be realized as some other morphism. So the situation is that combining some work of Dean and myself and some work of David Bessis, we know this because we show that if we know that two roots are conjugated in the braid group, then they are in the same component of this category by using the notion of Garside categories, actually. So it's something that we have been working with Dan Kramer and David Bessis, Dean and myself. We have a notion which generalizes Garside monoid, which is Garside category. This category is a Garside category, and using that, we could show that if the roots are conjugate, they are in the same corner of the category. And David Bessis was able to show that actually two roots are conjugate in the braid group. And actually, that is a side effect of a very nice theorem he proved. So there was a conjecture that this configuration space corresponding to the braid group of a complex coefficient group, it was conjecture it is a K-pi1 space. So this was proved by Deligne in the case of finite Coxeter groups, but it was a conjecture in general. And recently, maybe 2-3 years ago, David Bessis proved this in a very nice paper that you can find in archive. And in this paper, it showed also that two roots of the same order are conjugate, and that the centralizer of a root is isomorphic to the Brett group of the complex efficient group. So by combining these two theorems, we have the first two parts. Okay, now for the third part, so if I have time, I will explain a little bit of some work with Digne, Rocky, and myself, where we can show that this is true, for instance, for all roots in case of GLN, and quite a few other cases, that it factors through cyclotomic algebras. So this is via a technique which reduces the problem when we have a cyclic centralizer. You have to compute something in that case, and then you can deduce a theorem in general. Okay, using the same techniques, we could show that the alternating sum gives a trace even less. So in GLN, we could prove it when D is 1, 2, or the Coxeter number. And now the hardest part is to prove that the cohomology group are disjoint. So actually, you need to compute exactly the cohomology group to do that. And computing the L-adic cohomology of a variety is a difficult problem. Only feasible if the variety is of small dimension. And the case of the smallest dimension is when you take D, the Coxeter number, then the dimension of the variety is just the rank of the group. And actually, this was done by Lusztig to compute the cohomology in this case. And apart from this case of the Coxeter number and a few other cases where the dimension is small, the last part is very difficult. Maybe I won't have time to go very far, but I want to illustrate one particular case of the conjecture, which is quite interesting. Take D equal 1. So D equal 1 corresponds to take a what people call linear prime. So you take a prime which divides Q minus 1. In this case, the Brouwer conjecture was known by some work of Puch, where he found that there was a Morita equivalent in this case, which was realized by taking the ordinary Hecke algebra. So in this case, you take just its variety. It is the cohomology complex of the Deligne variety x1, if you want, corresponding to the element 1 of the Weyl group. And in this case, he found a Morita equivalence using that the endomorphism of this induced representation is the ordinary Hecke algebra. Okay, but if we follow the general conjecture, we should conjecture something slightly different. We should consider, since we take this root of pi, we should just take pi itself. So with this construction of Deligne, there is a variety x pi, which is just this variety of pairs of Borel subgroup, where position in W naught, and B2 is also in position W naught with the Frobenius of B1. And the conjecture says that the Hecke algebra should also be the endomorphism algebra of this variety of a large dimension. So actually, we can prove something. Okay, we cannot compute the cohomology of the variety. It's very difficult to compute the cohomology group of a variety of big dimension. But what we can do is at least make the Brett group, Brett monoid act on this variety and show that it factors through the Hecke algebra. So actually, we can also show that the alternating trace is the canonical trace of the algebra. But there is a twist here, because we first thought that it was exactly the ordinary Hecke algebra, but in the E7 and E8, you can see that it's not exactly the usual Hecke algebra, because when you have the endomorphism of the variety G over B or X1, to define an endomorphism, to define an isomorphism between the Hecke algebra and the algebra of the Weyl group, since the algebra splits only over square root of Q, you actually must choose the square root of Q. And if you change the square root of Q, you don't see any difference, except in E7 and E8, when you have these characters of the Hecke algebra, which actually are only defined over square root of Q, it does make a difference between the correspondence of character of the Hecke algebra and the Val group. And we saw that the correspondence was twisted in E7 and E8. So actually, it's a kind of Galois twisted version of the Hecke algebra that you have here. Okay, and so to prove these theorems, we had to use this technique of reducing to the cyclic case, and actually compute completely the cohomology group of this variety x pi when G is of rank 1 of 2. And already that is quite difficult because, for instance, for G2, this variety x pi is of dimension 12, and already computing the cohomology groups of a variety of dimension 12 is not easy. But we managed to do that, and that's how we prove that the Hecke algebra, well, the action of the braid monoid factors through the Hecke algebra when you go here. And so I point that you have something interesting here. So you have a graded version of the Hecke algebra. This endomorphism is graded. And so you have a graded version where here I wrote in which degree some character should occur. So it's something to study. Okay, I see I'm almost finished, but I think, okay, I will just try to explain a little bit how you can reduce to the cyclic case. So you want to show that this dx we have constructed factors for a cyclotomic Hecke algebra. So you have two things to check. You have to check the braid relations. That will be very easy because we had an action of the braid monoid. So there's basically nothing to check. So checking them just means proving this theorem I mentioned, that the endomorphism in the category is really actually the right monoid. Okay, the difficult thing to check is these polynomial relations. And so I don't want even to check them, but just to make some reduction theorem, where you can reduce to a smaller group where the group, the centralizer is cyclic. Okay, and so actually what we could show is that if you take one of these braid reflections which generate this braid group of a complex reflection group, and if you look at the cyclic subgroup which one of these braid reflections generate, you can always opt to conjugation. Well, I don't have a general theorem, but it seems that in practice you can always do it. And but I don't have a general theorem about that. But I know of no counterexample to this statement, that you can always find some subset of the generators, some standard parabolic subgroup, such that this cyclic subgroup is actually equal to the centralizer in a parabolic subgroup. So we start with this situation. We assume that we have a cyclic group by taking the centralizer in a smaller subgroup. And actually, we want to have a reduction corresponding to this subset. So what we could show, so if you have this situation, we'll have that this element will normalize this subgroup. And in this situation, we can show that if the element we take in the braid group normalize the subgroup, then the variety can decompose in two parts. So there is the action of G is seen on some intermediate variety, and then you have a similar variety for a Levy subgroup. And here, the element you take in the Levy subgroup is the longest element in this parabolic subgroup of the braid group, which divides the element you started with. So you can show that if you take a parabolic subgroup of the braid group, it always exists. There is always the longest element which divides. And the Frobenius on the Levy subgroup correspond to the rest of the elements. So in this situation, basically, you can reduce the theorem you started with to prove the same theorem for this variety of the Levy subgroup. And hopefully, this variety is of much smaller dimension. So this is basically the techniques we have. Okay, I think I should stop because I'm going quite fast, and the rest is also technical, so there's no point in going on. Okay.
Questions? Is it possible to say in a few words what a Garside category is?
Well, you know what is Garside monoid?
Not really.
Maybe I should explain. Well, maybe I need 5 to 10 minutes. Can I put this up so I do the blackboard? How do you lift the thing?
I don't know.
Okay, I can. We are right here. Okay. Well, watching. Well, if you take so the positive Breit monoid, so the Breit group is generated by this with the relations. Okay, you take this as a presentation of a monoid, and you get the Breit monoid. But now, okay, it is a Garside monoid, and Garside monoid means the following. So when you have a monoid like this, there is a notion of divisibility. You say that the x divides y. If xy inverse, x inverse y is still in the Breit monoid. So you have a notion of divisibility. With this notion, you can find that the lift I have taken of the Weil group is exactly the same as the element in the Breit monoid, which divide the lift of W node. The same thing. Okay, and using that, you have also a second thing that you need to know, that you can show that if you take any element in the Breit monoid, there exists a unique longest element, which I will call alpha of b, which is in this section called radius, and such that alpha of b divides b. Okay, and there is a paper by Garside in 1969 where he proved many nice properties of the Breit group, starting just from these facts. So from these facts, what you can do, for instance, you can find a normal form for element of the Breit monoid. What you do, you take an element b, and then you look at the longest element, which is radius divides b. You call this b1. Now you take what's left of b and you apply it. You get b2 by taking the longest element and so on. And so you have a decomposition of b in terms of products of reduced world, and which is canonical, so it's a normal form. Once you have normal form, you can do many things, compare elements. You could find an algorithm for the conjugacy problem, for instance, using that. You have many things you can do. Okay, and so to abstract this situation, you assume that you have a monoid which has the following property. So what is a Garside monoid? It's a monoid where you have a set, they call it P, of simples. So this set P will correspond to this section W, which has a property that P, so a monoid M, say, P generates M. And second thing, that P is the same thing as the divisors of a special element. So P is all the x in M, such as x divides something called delta. It's called the Garside element. So in this case, you take W naught. And, oh yeah, you ask that the monoid is cancellative. That is, you ask that when you have xz equals yz, then x equals y. Okay, and the only thing additional you ask is that this P is a lattice for divisibility. That is, there are GCDs and LCM. Okay, and when you have this, you can follow all the things that Garside proved. For instance, just from this fact, you can prove that the monoid embeds into the group is torsion-free, many things you can prove about the Braid group.
And
Okay.
all braid monoids are Garside.
So the Braid monoids of finite Coxeter groups, they are all like this.
Only of finite.
Because if it's not finite, you still have a similar structure, but you don't have LCMs. You still have a GCD, but you may not have LCMs. But there's something called, I think, what is called it, partially Garside, whatever, but yeah, there is something called, maybe some people now call it Garside, but it's a variation, where you don't ask that elements have LCM, but you ask if they have common multiples, they have an LCM. And then many properties work. But what you can still not prove is that the monoid embeds into the group. For the monoid to embed into the group, you really need to have LCMs. So actually, for these Braid monoids of infinite Coxeter groups, we understand very well the Braid monoid. But the group is more difficult because we understand very well the monoid. It has a structure corresponding to this. But we cannot show that the monoid embeds into the group. So the group is still a problem. But this works also for monoids of infinite Coxeter groups.
Is W a Weil group or a complex reflection?
So here I was talking about finite Coxeter group. So it's more general than Weil group, but it's less general than the complex reflection group.
W is a Coxeter group.
Finite Coxeter group. Okay. But this construction actually became much more important after the work of Biermann, Cohen, Lie, because this is a monoid for the Braid group, and Biermann, Cohen, Lie in 1998 found another completely different monoid for the Braid group, which was also Garside, but it's quite different. And actually, it's quite simple to explain. So this presentation of the Braid group corresponding to this, you can describe a bit abstractly. So you have the following presentation of the Braid group. You have a set of generator, which is in bijection with W, and the relations are that you have AB equals C if actually in W the length we're adding. If you add this, then you put this as a relation into the. So you take the abstract monoid generated by a set in bijection with W, and with only relation this, you get the Braid monoid. Okay. Now I will tell you what is the Biermann-Coley presentation. It's quite different. So here, this corresponds to choosing, when I say the length, it's the length with respect to the set of generator S you have chosen. Now, if you have a group and a set of generators, this gives you a length function. Now, take W, but take instead all the reflections, not only the Coxeter generator, you take all the reflections. You get a different length function, which is smaller. An element of maximal length for the smaller length is a Coxeter element. Okay, and now in the same, we'll define a divisibility relation, which is that x divides y. If you can write y is xz, and the length add.
Is X what? C. Now what is that?
So I take a Coxeter element.
Yes.
I say it's of maximal length with respect to the, if you take all the reflections.
But what's written underneath? XC, XV.
Sorry? I say that whenever you have a set of generator, you have a length function and a divisibility relation. You say that it divides when the lengths add. And now I will not look at all of W as in the previous instance, but I will take a P, and P is all the elements. P is all the elements in W which divide C with respect to this order, this divisibility coming from this generating set. Okay, so in the case of type A, for instance, the set of elements P is in bijection with the non-crossing partitions, and the number is Catalan number. But now I just mimic my definition. I take the monoid generated by P, and I put as relation AB equals C whenever the length, but this time with respect to this different length function, add. I get still a presentation of the braid monoid. So for type A, this was a discovery of Berman-Colley, and it was generalized by David Bessis to other finite Coxeter groups, and he called this monoid the dual braid monoid. And what is interesting is that this works also for the well-generated complex reflection groups. So this cannot be extended to complex reflection group, but the second construction, it happens to work also for the well-generated complex reflection groups.
So what are the roots? And the roots are
There are no roots. I'm not talking about roots. I'm talking about generators of a group. Where do you see the roots?
well, but to define the length function, you needed
No.
the
the minimum number of generators.
which were different than the simple.
The length is the minimum number of generators used. Where do you see roots?
Because you have to use the non-simple reflections.
I mean, the non-simple reflection is a conjugate of a simple reflection.
Okay. If you want to say
I want to say whatever makes sense.
that. Well, you didn't define.
So is it the case that the non-well-generated complex reflection groups, that the braid groups of non-well-generated complex reflection groups are not known to have Garside monoids?
No, but they have Garside categories.
Okay.
I did not say what is a Garside category.
Okay.
So a Garside category is a same kind of definition, but in categories. Because if you remember, I started from a variety attached to an element of the Val group, and then consider a category. And you can have similar definitions for category. You have a category which is generated by a subset of morphism, which is cancellative, and you are starting from an object. There is a unique longest morphism called delta. Well, you can have the same formalism in categories, and this is suited to this problem and what it used to.
Well, another question, just a general question. So you have a complex reflection group. The invariants are polynomial.
Yes.
Right. Does that correspond, like Chevalet's theorem, to the polynomial invariance for an infinite group?
Sorry?
Does that correspond to the invariance of any infinite group being polynomial?
What do you mean? How in Chevalier theorem do you see something like that?
Well, I mean, the invariance under the complex semi-simple Lie group of the symmetric algebra maps isomorphically to the invariance under the violent group of acting on its standard representation.
Yeah, okay.
Right?
We don't know how to construct Lie algebras with Val group in a complex reflection group. That's a topic of study. Actually, probably it doesn't exist. Doesn't exist such a algebra, but maybe there is some categories of representations or something like that. Oh no.
Any other questions or comments? So if not, let's thank the speaker again.